Welcome to another live session for the online course. Chris Impey, and ready to take your questions. It's hot here, it's the tail end of summer. They say the planet is warming, and I guess we feel it in Tucson at least. Ready for your questions.
All right, thank you everybody for joining us. The first question is from Robert Brady, who sent an email in, and he would like to know, does the Big Bang theory include or exclude dark energy and dark matter?
Yeah, good question. A Big Bang is the currently accepted model for the creation of the universe in a hot, dense state 13.8 billion years ago, with a lot of evidence to support it. It's a very well affirmed theory in cosmology. And yes, the Big Bang is the creation of all space and time in an instantaneous event. And so it, by definition, includes dark energy and dark matter. However, it's important to note that the dark energy and the dark matter actually have very little influence on the universe in its early stages. So the universe is obviously expanding extremely fast. The distance or the speed at which points in space-time are moving apart in the first tens of thousands of years, a few 100,000 years, is far greater than the speed of light. And the dynamics of that explosion are dominated by the energy in the initial impulse. Dark energy, the accelerating repulsive entity in the vacuum of space that's causing the current acceleration of the universe, doesn't start to dominate the cosmic expansion until about 5 billion years ago. So 2/3 of the way out in the history to this point. And then in those very early stages, dark energy really doesn't factor in. It is present, however, in the entire universe all the way through its history. It just doesn't dominate the dynamics. And the same is at some level true of dark matter. Dark matter, of course, represents the bulk of the mass of the universe, so the early deceleration of the cosmic expansion is in fact governed by dark matter, more than normal matter, which is about 1/5 or 1/6 as much as dark matter. But dark matter also has very weak interactions with normal matter and radiation. Probably doesn't interact with the electromagnetic force. So its interactions between different parts of the universe in dark matter are also weak or non-existent. And all it's doing is acting as a decelerating entity in the universe for the first 2/3 of its expansion until dark energy takes over and becomes the dominant agent. Ready for your next question?
All right, thanks, Chris. The next question is, how was matter, like hydrogen, helium, created after the Big Bang?
So matter is actually a tiny component of the universe in the Big Bang model. Because if we look at the present-day universe, the old, cold, and large universe, there are a few 100 million photons for every particle, either dark matter or normal matter. And most of those particles, of course, are hydrogen atoms, second most helium atoms. So 99% of the universe is hydrogen or helium, the two simplest atoms. But there's hundreds of millions of photons for every particle. So the universe is dominated by radiation. We don't see or feel that because in the large, old, and cold universe, that radiation is very feeble. It's microwaves. It's the microwave background, the evidence we had for the Big Bang that was first measured in 1964. But if you wind the clock back to when the universe was smaller, hotter, and denser, then the radiation dominated. And formally, in physics terms, at all points up until about 10,000 years after the Big Bang, the universe was radiation dominated. So the radiation really dominated what the universe was doing. Matter only began to dominate after 10,000 years, and so only after 10,000 years could the smooth chaos of the universe be modulated by gravitational interactions in the formation of structure. Ready for the next question?
Right. The next question is... Sorry, we're just trying to troubleshoot that little echo that everybody hears in our sound. The next question is from from an email that asks, can you talk about the angular momentum of the Earth and the orbit around the sun? Is angular momentum conserved in that case as well? And how does that work, and how does that affect the Earth's orbit?
Right, so the Earth and all the planets in the solar system have angular momentum due to their spin. And the Earth was formed from a material at about this radius from the Sun, 150 million kilometers out from the Sun, in the very early history of the solar system, so 4.5 billion years ago. And so the material out of which the Earth formed had the angular momentum of a disk of dust and gas at a distance of 150 million kilometers from the infant Sun. And the spinning Earth contains that angular momentum. So when we say angular momentum is conserved, when mass configurations change, the total angular momentum must stay the same. So the angular momentum of all those tiny dust particles and gas particles orbiting a band of material around the Sun before the Earth formed does equal the angular momentum of the Earth itself. And the Earth itself spins in the same direction as its orbit around the Sun, indicating that the angular momentum vector has not changed. So angular momentum is conserved in solar system evolution. If it does not appear to be conserved, it's usually because of an external interaction. So for example, Venus, the counter-rotating planet in the solar system, which spins in the opposite direction to its orbit around the Sun, is imputed to have had a collision or an interaction early in the history of the solar system that injected angular momentum and gave it an opposite direction of its angular momentum vector. Ready for the next question?
Thanks, Chris. The next question is from Valerie, who sent an email. And Valerie asks, what are the chances that the recently announced NASA mission to Europa will find evidence of life in our solar system?
The Europa Clipper, it's actually undergone several name changes, is an ambitious mission that will take its data over a decade from now. So these are long time scale missions. It's basically an orbiter, but its most aggressive feature, if you like, will be launching projectile to the icy surface of Europa, splashing off material by its impact, and then in a subsequent orbit using spectrometers to sniff the icy particles that were splashed off the surface. So that spectroscopy is about as close as the Clipper mission is going to come to being able to detect life. And it's not really that close. This is not a true biological life detection experiment, the like of which we're envisaging for Mars maybe in a decade from now. It's closer to what was done with Enceladus, the moon of Saturn, which the Cassini mission detected icy particles from the jets and was able to detect salt and organic compounds in those icy jets. So the Europa mission will presumably do the same thing. It'll do spectroscopy, it'll look for organic materials and hopefully complex organic compounds, perhaps the precursors of life, perhaps amino acids in the material from the surface of this icy moon. That's not clear what it will find because the icy surface, probably only projecting materials from a few meters down, is exposed to intense cosmic rays. So there's no hope that biological organisms could exist in this heavily irradiated and super cold hard ice surface. Splashing material from maybe a meter or two under the surface has the potential maybe to detect organic compounds, but most people don't think it will find life. And it's not really a true life detection experiment in the sense that it could not look for nucleic acids or replicating molecules like RNA or DNA. Ready for the next question?
All right, the next question is from one of our live viewers, Gabriel Lopes, who asks, I've taken up stargazing about a year ago. Do astronomers usually like stargazing themselves? And how knowledgeable are astronomers generally about the celestial sphere?
Astronomers do like to stargaze themselves if they're able to. Astronomers, of course, are in the same boat as most people in the United States and most urban parts of Europe, where they're in suburbs or cities where the sky is not suitably dark. I have that problem. I live in Tucson. Tucson is a place with lighting ordinances to try and keep the light pollution to a minimum, but if you live in the city, you're just not going to see much. So astronomers live in places where they have to travel to go out and see a dark sky just like everyone else. And I and others, if we can do that, we choose to. I have an amateur astronomer that's a neighbor of mine, and I like to go out and use her telescope, or she invites us to look at her telescope, and even from the backyard in a suburb, it's pretty good view. But to the second question, I would probably say that the average professional astronomer does not know the sky or the celestial sphere nearly as well as the average amateur astronomer. They might know the constellations and the very basics of the night sky, but in terms of deep sky observations or navigating from deep sky object to deep sky object, the average amateur astronomer, just by their knowledgeable. Ready for the next question.
All right, the next question.
Familiarity and their dedication to their craft is actually much more knowledgeable.
You have a whole new kind of universe inside of a black hole.
It would be interesting. We imagine that a black hole whose contents are unknown to us because information cannot escape. Obviously, the black hole contains all of the stuff that went into the black hole and that fell into it over its lifetime. This is normal mass, maybe complete stars, maybe planets, maybe just simple particles, grains of sand, dust, rocks, and gas particles. So it's unlikely to be in any ordered form. Whatever the contents of a black hole are, it's sort of disordered, chaotic matter. So it's probably not appropriate to think of a universe within a black hole. It's a super dense, unimaginably dense state of normal matter that's fallen into the black hole, crushed down to nuclear densities, essentially. And this is not a place where a human could survive. This is not a place where we could investigate it, where you could travel within the event horizon freely. So in that sense, it's not like a universe at all. Ready for the next question.
Thanks, Chris. The next question is from a question that we got through email from Bill Riddle, who asks, Chris implied in a recent talk that string theory was falling out of favor with cosmologists. If so, what has replaced this theory and what's exciting to theorists now?
String theory has fallen out of favor, not just with cosmologists, but also with physicists who gave birth to string theory in the early 1980s. String theory is a product of physics trying to understand the fundamental nature of matter below the level of quarks and electrons that we're familiar with in standard particle physics. String theory is disappointing to physicists as well as cosmologists because it hasn't delivered on some of its incredible promise. In part, that's because the theory is extremely difficult to work with and calculate in. So maybe it's just a question of patience. Maybe string theory only being a few decades old, we just have to work harder on the theory. It still has some appealing elements. Some of these are aesthetic. They're at the level of aesthetics in physics. Beauty and symmetry and elegance in the theory, mathematically and physically, is generally agreed by most physicists. And the question of what could replace string theory as a theory of how matter works and how the universe works is really there's no other contender that has the attractive features of string theory. People are looking at alternate theories of gravity that will somehow resolve the disconnect between general relativity and quantum theory. But those theories of gravity are also extremely difficult to work with, and really very few people, a few dozen clever theorists are working with them. So no other theory of fundamental nature of matter and gravity has achieved as much traction or effort as string theory. And so at the moment, we're kind of stuck on that score. Ready for the next question.
All right, the next question is from Alexis Frey, who's on with us live. And Alexis would like to know, could the material in Saturn's rings collapse back into a moon?
Unlikely. The material that we see in the rings of all the giant planets, remember Saturn has the most prominent rings, but all the four gas giants have ring systems. But just take Saturn because it is the most prominent and the largest amount of material. If you swept all that material up and crushed it back into a single object, it probably didn't start as a single object anyway. It would be very small. It would be the mass of one of the very smallest moons of Saturn. So it is unlikely that was the origination. It's leftover material from the disk out of which Saturn formed, a miniaturized version of the disk that the solar system formed from. And so some people call it a failed moon, the ring systems, because they're so much less than the mass of a normal moon. It's possible that they were disrupted, that a minor moon formed and then was disrupted gravitationally by tidal forces and splintered into pieces. There's also recent evidence that the ring systems of Saturn and probably the other gas giants are actually recent occurrences, that they were not present at the formation, and they formed in the last few 100 million years. That's new and slightly controversial research, but would be very interesting as far as a theory of how the rings formed. Ready for the next question.
Thank you, Chris. The next question is from Natasha Jardine, who's on with us live, who asks, is it possible for a planet to be in a stable orbit around a black hole? If so, could a spaceship theoretically land on such a planet?
Definitely. It's possible for a planet to be in a stable orbit around a black hole. And the question really is, how far would the planet have to be? If the planet is very close to the black hole, by which I mean a few times the event horizon distance, then it would be subject to loss of orbital energy by gravitational radiation and dynamical friction, and would spiral into the black hole. So there are stable orbits very close to a black hole, but there are subtle dynamical effects that would lead to them not being long-term stable. That is to say, stable for maybe hundreds of millions of years. But for a localized experiment of a spaceship in orbit around a black hole, yes, you could orbit close to a black hole. You'd be subject to incredibly intense gravity and also strong tidal forces. The same tidal forces that would rip a person or a normal physical object apart falling into a black hole would also exert extremely strong tidal forces a few times as far as child radius out. And so a person in a spaceship would not survive that. Probably the closest an astronaut in a hypothetical spacecraft around a black hole could survive is about 20 times the event horizon distance. Ready for the next question.
All right, our next question is from Yuki Mikami, who's on with us live, who asks, do you think Tabby's star is a Dyson sphere?
So Tabby's star, for those who don't know, is a nickname for a star whose technical name I'm not going to remember, it's now alphabet soup designation, is a star that showed a very erratic and very strange light curve. The light curve is the way the light from the star varies over time when you monitor it. And this particular star showed strong variability and extremely rapid changes in brightness. A jagged light curve, if you like, with vertical changes from high brightness to low brightness in very short times, and no particular pattern or repeatability to it. Fascinating data, and not consistent with known variable stars, led to the speculation, of course, that this is an artificial object, that there's some physical structure that was causing the star to occult, and that structure might be something like a Dyson sphere. Dyson sphere is an energy trapping sphere that could be built around a star in principle by an advanced civilization to harvest energy. Now, Dyson spheres can't actually be solid objects because the tidal forces and stresses would break them apart. So they'd have to be a loose sort of trellis work of a structure. As for whether Tabby's star is a Dyson sphere, I think the evidence is now pretty strongly against that. We don't fully understand the normal astrophysical processes that could give rise to those variations, but there's no particular reason to fall into this very strong hypothesis that this is an alien civilization trapping that star's energy. Ready for the next question.
The next question is from a live viewer, Friedel, who asks, theoretically, could dark matter and or dark energy be drawn into a black hole?
Yes. Black holes exert gravity on all matter and, of course, on radiation. The definition of a black hole is an object from which radiation cannot escape due to the intense gravity. So since a black hole traps everything, it would trap dark matter. Let me make a little asterisk on dark energy. So for sure, dark matter would be trapped in a black hole, regardless of the nature of the dark matter particle, which we don't understand at the moment, and regardless of whether that's a fundamental particle moving at close to the speed of light, as in hot dark matter, or below speed of light, as in cold dark matter. Yes, dark matter would be trapped inside the black hole. Dark energy, however, is something different. Dark energy is a force or an entity or a negative pressure, more correctly in physics terms, that operates in the vacuum of space. Since black holes distort space-time, but they actually don't alter the vacuum composition of space-time, dark energy is fairly immune from the influence of a black hole, as well as we understand dark energy, which is not very well. Ready for the next question.
All right, the next question is from James, who sent an email. And James asks, I have heard that because the heavy metals are only produced in a supernova explosion, the Earth must have been formed from such an event. Is there any other evidence there was a supernova in our part of the galaxy? Are there any estimates when that supernova may have occurred?
Yes, there are indications of supernovae in the nearby part of the universe to the Earth. However, relative to the initial question, it's not strictly true that most or all heavy elements are produced inside supernovae. Substantial number of heavy elements, amounting to maybe half or more, are caused by collisions of neutron stars and also by heavy element production in the atmospheres of evolved stars, where neutron capture, a less dramatic process than occurs in a supernovae, can gradually ratchet up the atomic number of elements even up to the transuranics. So significant number of heavy elements are caused in a rather more mundane process than a supernova, and then the rest are in the death of individual massive stars and in the collisions of neutron stars. That's new information in the last few years to know that neutron star collisions produce heavy elements. So those heavy elements are indeed produced from previous generations of stars, and so they must have pre-existed when the Earth formed 4.5 billion years ago. In terms of localizing the events that led to the heavy elements of which the Earth is composed, and our bodies by extension, that's extremely difficult to do because all traces of the explosion have long since gone. Remember, because these elements were created at least 4.5 billion years ago. And for example, the orbital period at the distance of the Earth from the center of the Milky Way is 250 million years. So the Earth has orbited the Sun and the center of the galaxy over a dozen times since those heavy elements formed, and that sort of scrambles the positions of nearby stars. And the dead stars, their remnants, black holes and neutron stars, are hard to find anyway. So there's really no way to do the archaeology to locate supernovae. There's interesting research, however, that does indicate supernova going off in the relatively recent history on the Earth. We see the injection of heavy elements of radioactive iron and nickel, radioactive versions of these stable nuclides that only are created in supernovae, and sometimes high spikes of abundance of these radioactive elements are seen in ice sheets and in core samples of the Earth at ages of a few million to 5 or 10 million years ago. So there's a small emergent field of research that tries to impute local supernovae, that is supernovae within probably a few hundred light years of the Earth, that have gone off in the relatively recent geological past, like a few million years. It's slightly controversial research, and it still doesn't allow you to identify the star remnant that caused that event, but it's starting to home in on how many of these supernovae they were and how much of the heavy elements of the Earth were produced by them. Ready for the next question.
All right, thanks, Chris. Mohan Malhotra, who's on with us live, asks, what are fast radio bursts, and what do you think of the fast radio signals that were reported recently?
So fast radio bursts were a mysterious phenomenon that didn't really have an explanation until fairly recently. It's still not fully understood. These are pulses, radio pulses, typically low frequencies, millimeter to centimeter wavelengths seen by radio telescopes. And they literally last a few seconds or even small fractions of a second and then trail off. And when you look at the position on the sky, radio telescopes don't typically pinpoint objects, especially if they're far away, accurately enough to identify. They didn't tend to have identifications. So it therefore was very hard to say what kind of object was producing this. Now, more accurate radio observations, and just in the last year or so, have allowed the identification of the optical counterparts to fast radio bursts. And now it does appear that some of these radio bursts, they probably are not all one phenomena, just like gamma ray bursts, it turns out, are not a single phenomenon. So fast radio bursts are probably a small variety of astrophysical events, but some of them at least are caused by stellar collapse, sort of collapsar model of a giant star as it dies in a supernova event or something like that. Formation of a magnetized star, because that magnetic star formation from the magnetic field that amplifies during collapse can lead to radio emission, as in a pulsar. So there are now a small set of objects where we're starting to understand what causes the fast radio burst, and they are indeed stellar cataclysms near the end of a star's life. Ready for the next question?
Next question is from Lalit Wadhwa, who is on with us live, who asks, could you please share your views on the inconsistency of Hubble constant measurements from different techniques? What could be the reasons that we are ending up with disparate results?
So the Hubble constant is the current expansion rate of the universe, measured in kilometers per second per megaparsec. So it's how fast galaxies are moving away from each other per million parsecs of distance from the Earth. So the further away the galaxies, the faster they're moving away from each other. Measurements of the Hubble constant have classically been done with using standard candles, as they're called, or standard light bulbs, so supernovae or Cepheid variables or brightest giant stars or some other metric, looking at how the brightness of these particular objects appears to change with distance. This process, where you step your way out in the universe from nearby galaxies to galaxies maybe tens of millions of light years away, has produced a Hubble constant of a certain value. That number was uncertain. For a long time it was a factor of 2 uncertain, then 30%, then 10%. The Hubble Space Telescope key project lowered the error bar down to about 7%, and since then it's come down to about 3 or 4%. So that's one measurement of the local expansion rate. An entirely independent measurement of the expansion rate comes from cosmological measurements, because our model of the expansion of the universe leads to a very well-known age, and our knowledge of the dark matter and dark energy density shows what the expansion history of the universe might be, and that of course allows you to play out what the current expansion rate is. And doing that method, that second method, through a cosmological model leads to a number that's a little different. It's not a big difference, less than 10% or about 10%, but it appears to be statistically significant. And this is the source of the current controversy. And in a recent conference that gathered together the people working on both methods, there was no clear resolution of this issue. There are two likely outcomes of this situation. One is the radical outcome that there's new physics to be taken care of, and that typically would mean that in the cosmological measurement there's a new entity there that's causing the discrepancy, and it's something about the basic dynamics of the universe we don't understand. The more mundane, and actually in historical terms in astronomy more likely, explanation is that one or other method has systematic error that's been underestimated. And the history of the Hubble constant measurement over decades has shown that many times people underestimated their systematic errors. So that's what I would put my money on. Ready for the next question?
All right, the next question is from Gabriel Lopes, who is on with us live, who asks, are there any plans to use that crazy big telescope network that took the black hole photo and aiming it at something a lot closer to get a good view of it, maybe a star like Proxima Centauri?
Yes, so the Event Horizon Telescope, which was the array of radio telescopes that was used spectacularly earlier this year to get a picture of the M87 black hole, a 6 billion solar mass black hole, about 60 million light years away. That array is indeed already being used on other targets. The nearest black hole target is likely to be not a stellar black hole, but the massive black hole in the center of our own galaxy. If you work out the next best target for that telescope in terms of resolving the event horizon, or being able to see the size of the event horizon and look at the shadowing in radio waves, the galactic center black hole is the next best bet. So it's likely that there's already an image of that in existence, and they're just working on making it look nice and understanding all the errors and publishing a paper. The Event Horizon Telescope could look at objects closer. It could look at very small black holes, stellar mass black holes closer, but it turns out that the nearest of those stellar mass black holes is hundreds of light years away, maybe a few thousand light years away. And the Event Horizon Telescope doesn't have the sharpness of vision to really see those event horizons. It turns out you're better off looking for a very much more massive black hole that's not vastly further away. You do better looking at it that way. So the Event Horizon Telescope beyond the galactic center will be used to look at other active galaxies like M87 at distances of maybe a few, up to a few tens of millions of light years. Ready for the next question.
Right, the next question comes from a live viewer who asks, can we actually build a telescope a bit further out in space and focus the sun's huge gravitational lensing effect to magnify other objects or other worlds?
It's an interesting idea to use the natural force of gravity as a lensing system. The trouble is that the sun is a relatively small and not very high density object, so its ability to deflect light is very modest. The deflection of sunlight as it grazes the sun's limb is only a few seconds of arc. That was the basis of Eddington's eclipse expedition in 1919 that confirmed general relativity. That's a very small deflection, and that's unfortunately not really a big enough deflection to make a good lensing experiment. It's just too subtle an effect. So we need a more massive object or a much longer lever arm to actually do gravitational lensing using a single star that's not collapsed like the sun. It's possible to use objects in space as natural gravitational lenses, and astronomers do that all the time. They find dense objects or sometimes just big concentrations of dark matter, and they use those directions of the sky to opportunistically identify a lens and then magnify the light from distant regions. But doing that close to the Earth turns out to be not very practical. Ready for the next question.
Right, the next question is from Nidish Sharma, who asks if you can explain quantum entanglement, and without using a sock example, I'm not sure what that is, but can you explain quantum entanglement?
So quantum entanglement is the ability to create, it occurs naturally too in some instances, but to create in the lab quantum states that are coherent over some physical distance that's larger than an atom. This is typically done in what are called split photon experiments. That's where you have a light beam that's passing through a half-silvered mirror, and you separate the light beam into different directions and then recombine the light at the end of the experiment. In principle, since light is a wave but also a particle, you can take the intensity of your light beam down to the level of single photons. And so logically, therefore, you have created a coherent, coupled situation where the light travels simultaneously down two paths. And that's essentially the definition of entanglement, because the two remote states are entangled. They relate to each other, even though they have physical distance between them. It's a strange concept because it implies non-localized physics. It means that the information of the coherence must be maintained somehow instantaneously and not transmitted at the speed of light. So that's the quantum entanglement we can demonstrate in the lab. Originally, those experiments were first done by Alan Aspect and others in France in the 70s and 80s. Now, with more tightly engineered systems, creating entangled states, especially for very cold situations of atoms and molecules, is routinely done in the lab. And of course, the vanguard or frontier of this work is to try and do computation using these entangled states. And just in the last month or so, a couple of labs, actually, one in the US, one in Japan, were able to create 8-qubit quantum computers. And a qubit is an entangled quantum state that allows you, instead of the ones and zeros of standard binary logic, to actually have a third entangled state that's neither one nor zero. It's a combination of the two. And theory shows that doing computation with qubits or entangled states is much more efficient than doing it with simple binary 1-0 logic. So that's the sort of frontier of quantum entanglement, where we can engineer those entangled states and actually do computation with them in a quantum computer. Very rudimentary version of a computer, but it's very exciting. Ready for the next question?
All right, Chris, the next question is from Wendy, who sent an email asking, what's the latest understanding of dark energy? Is it expanding in space as space expands, or is it part of space itself?
Dark energy is a big unknown in cosmology. It's the biggest unknown. Dark matter is also not clearly identified as a subatomic particle, for example. But astronomers and physicists are sort of homing in on dark matter, and they're ruling out a lot of things. So people are confident that within 5 or 7 years we'll know a lot more. Dark energy, there's no such confidence. Dark energy is imputed to the vacuum of space. It's a characteristic of the vacuum, so it's nothing. It's a characteristic of nothing itself. It's a negative pressure in physics terms. Its equation of state makes space-time expand at an accelerating rate. And that's pretty much all we know. All astronomers have been able to add to this is the fact that as far as they can measure, the strength of dark energy does not vary with direction in space, so it's not anisotropic. And there's no indication so far that dark energy's intrinsic strength in any unit of space-time varies with time either. So that's a sort of null result where we just don't learn anything particular or specific about dark energy. The next level of knowledge of dark energy is really quite challenging. There are very big surveys with future generations of telescopes that might tease out other attributes of dark energy, but at the moment physicists are kind of stuck. The theoretical speculation of dark energy would take a long time to describe, and so there are many papers written every year about that, but really no evidence to support any of those hypotheses. Ready for the next question?
All right, the next question is from Yuki, who's on with us live, who asks, should theoretical white holes be the end of a wormhole, and with the black hole being the start?
It's a possibility. The theorists who worked on black holes, and especially Stephen Hawking and Kip Thorne, Hawking is, of course, unfortunately passed away just a year or so ago, leaving Kip Thorne as probably the preeminent black hole theorist in the world. They speculated about a black hole potentially connecting to another part of the universe where the input of a black hole would release an output in the white hole at a different position in space-time, instantaneously connected by a wormhole through space-time. There's no evidence that our universe creates such situations. So they exist theoretically. They're not in violation of general relativity, to talk about that, and so that's why theorists are comfortable speculating about them. But our universe is very pedestrian in terms of its relatively smooth space-time curvature, so there's no indication of the convolutions of space-time that would be required to make a black hole white hole pair. So at the moment we have no evidence that they really exist. Ready for the next question?
All right, the next question is from Gitanjali, who asks, what happens after the stars burn out at the end of the universe? Will matter in the form of atoms and molecules still continue to exist? If not, where does it all go?
The speculation about the universe after the death of all stars is uncertain, because the physics idea in play here is that normal matter is not stable. So in grand unified theories that unify the three forces of nature except for gravity, the most favored of these grand unified theories, which has relatively sparse support for it experimentally, suggests that normal matter would not be stable. In other words, the proton, for example, would decay. We have experimental upper limits on proton decay because people have gathered together large tanks of fluid and have been staring at them for decades, and if the proton decay was significant, they would have measured them. So I think the proton decay limits are upward of 10 to the 35, maybe 10 to the 36 years. So if protons decay, they take an incredibly long time to do so. But the theory still expects, in grand unified theories, that protons will be unstable, normal matter unstable. And so that's the real end of stars as we know them, because even though there's no light from the star, it's still a coherent object made of atoms. But if those atoms start to decay, then they decay into smaller subatomic particles, neutrinos, antineutrinos, and very low energy photons. And those entities will dissipate. Neutrinos, of course, interacting very weakly with matter, and photons fleeing at the speed of light. So normal matter will indeed disintegrate if our current theories are correct. And that's a very long timescale process, but that's the dissipation of all matter into a sort of quasi-uniform situation of low energy radiation, neutrinos and antineutrinos and electrons. Ready for the next question?
The next question is from Diego, who's on with us live, who asks, why are the gas and dust that evaporate from comets left behind the forming tail? Shouldn't this continue to travel at the same speed as the comet, like an atmosphere?
Some of it does. So the comets have multiple components. One of the parts of a comet is its halo. And you can see this in some images of comets that come close to the Earth. So a comet has a nucleus that's a few kilometers across for a typical comet. Then it has a halo, and that halo is energized material caused by the sun's radiation that is indeed held to the comet by its gravity. Of course, some of it's high enough energy that it escapes from the object and flees off into space. So the halo is material that's partly bound, but some of which is escaping into space, meaning the comet is slowly evaporating. The tail is more material, which is trailed out by radiation pressure behind the comet, and that material is also slowly escaping. So the halo and tail of a comet are not stable entities. They represent the gradual loss of material from the comet. In particular, the loss of volatile material, which to astronomers represents the frozen gases that are contained in the comets, frozen gases like carbon dioxide, water, methane, ice. The comet, of course, is also made of rocky material, so it's gradually losing its volatile or frozen gases and liquids. Ready for the next question.
Thank you, Chris. The next question is from Hassan, who sent an email asking, what is the latest theory on the origin of Earth's water?
It's a controversial subject, and it's controversial because one of the characteristics of water that we can investigate that gives a clue to its origin is the fraction of the water that's in the deuterated form. So hydrogen, of course, is H2O, but if it's the heavy version of hydrogen bound to two oxygen molecules, or deuterated or heavy water, then that has a slightly different origin. And so we looked to compare the deuterated fraction of Earth water to what we see in comets. And if that deuterated fraction, which is about 1 part in 10 to the 5 of normal water, matches that of a comet, then it's a good bet that that water was put there by comets in the distant past. So comet measurements are a little confusing because they're all over the place. I think only 3 or 4, maybe 4 comets have now had this measured directly by spacecraft and remote sensing. And they don't really tell a consistent story that matches the idea of the Earth being completely formed from comets onto the Earth, presumably coming onto the Earth early in the history of the solar system. The alternative theory is that the Earth's water was always deep inside it, was in deep rock, bound in deep rock, or in a highly pressurized, a sort of high pressure, high temperature, but trapped situation that gradually seeped out, evaporated out, bubbled out to the surface to form the Earth's oceans when the Earth was young. There's plenty of volume and mass for the Earth to have had this water, because remember, the sum of the Earth's oceans is a tiny fraction of the Earth's mass. We're talking about a tiny fraction of the total material. The idea of the Earth's water coming from the deep interior, as opposed to what's called the late veneer caused by comets and asteroids, it's unresolved. Both ideas are in play, and we'll need more measurements. We'll need better understanding of the Earth's interior, and also more measurements of cometary water to be able to resolve this question. Ready for the next question.
All right, the next question is from an email from Dan Vandenberg, who asks, how can we see back to the Big Bang if we are a product of the Big Bang? Isn't that light way out ahead of us, so to speak?
It's a good question. Where is the Big Bang? How do we see the Big Bang? And the answer is that we don't look out to the Big Bang. We're in the Big Bang. So the Big Bang is all around us. The evidence for the Big Bang is the microwave background radiation left over from the initial fireball that is cooled by the expansion of space-time over 13.8 billion years to a temperature of just under 3 Kelvin. And those photons are all around us with almost the same density in any region of space and the same intensity in any direction. So in a very real sense, the Big Bang is all around us. That direct evidence of the Big Bang is everywhere and permeates space. So there's no place for the Big Bang. The Big Bang is here and everywhere because, of course, the entire universe was part of this unfolding expansion of space-time. If we look out at physical objects in the universe, out in space and therefore back in time, we're also looking back towards the Big Bang. And what we see is the same in every direction. We see galaxies that look bluer and smaller as the universe was younger because the galaxies have been growing by mergers since then. Eventually, with the biggest telescopes, we see a time called the Dark Ages, before stars and galaxies formed at all. And the view of this is the same in every direction, because once again, as we reach towards the Big Bang with large telescopes, we're dealing with a situation that involves all space and time. So we would expect to see the same in every direction in space we look, and that's the case. Ready for the next question.
The next question is from Robert Baker, who's on with us live, who asks, could a black hole be made of a new form of condensed matter made up of compressed quarks? We know that neutron stars are sort of made this way from atomic bits.
Yes, physicists have speculated about quark matter for decades, and a lot of papers have been written about this. And indeed, neutron stars and pulsars could, at their cores, have a sort of loose version of quark matter. Quark matter is a situation whereby the pressure and density and temperature in the center, it's possible for quarks to be unconstrained. Normally, quarks are heavily bound into the atomic nucleus or into their constituent protons and neutrons, and we never see free quarks. In superdense states of matter and exotic states of matter, it's possible that quarks can be more loosely contained, if not completely unbound. And that's a speculation that applies to black holes too. The trouble is we have no way to interrogate the state of matter inside a black hole, and so there's no way to say whether the inside is made of quark matter. But the idea that quark matter could exist, theoretically, is fairly well established. Ready for the next question.
Tom also sent an email and would like to know what it means to say something like 1 minute after the Big Bang. Is time the same now as it was back then? Wouldn't time be extremely slow when the universe's density and presumably gravity are so high?
That's a good question. The general question behind this is interesting. Well, what does it mean to measure time early in the universe? We think we know what it means to measure time now. To come back and observe the universe a year later and see potentially everything slightly further apart, the universe very, very slightly colder, this makes sense. This is an understanding of time we're familiar with. But what does it mean when we measure time back to this instant of creation, the Big Bang? And the answer is that it's a very abstract version of time. In physics, it's called conformal time. This is the time axis of general relativity, of a calculation in general relativity. And in a cosmic sense, it's not like a clock. It's a very directly a function of the model of the universe. So all the model of the universe is telling us is what the mean density and temperature are some amount of conformal time after the Big Bang. And that's what the model expresses. It's not necessarily the time that would be kept by a clock, because clocks in different physical situations in the early universe would actually keep different time, would depend on their local gravity, since clocks run slower in strong gravity. So it really is a very abstract definition of time, really only meaningful within the mathematical model of general relativity explaining space-time expansion. Ready for the next question.
The next question is from Tony Lin, who sent an email asking, if a multiverse exists, could the accelerated expansion of our universe be due to the gravitational attraction of surrounding universes outside of our own moving towards us, rather than due to something unknown like dark energy?
If the multiverse hypothesis is correct, then potentially there are influences or impacts between universes that are beyond each other's horizon, or event horizon. That is, they're not in causal contact. The best people have come up with for those is that it could be a gravitational wave influence of another space-time on our space-time. It's unlikely that the influence of another space-time, separate from ours, causally distinct, would be felt in terms of any of the normal components of the universe, like particles, radiation, dark matter, and dark energy. So it is extremely difficult to come up with a testable prediction for a multiverse theory. That's been true for decades now. Ready for the next question?
All right. The next question is from Yuki again, who is on with us live, who asks, could microorganisms have come to Earth by an asteroid, as the panspermia theory says? How would we be able to test something like that to know if that's the case?
It's possible in principle. So we know that biological organisms, if they're entombed in rock, can survive for significant periods of time. There's speculation that they can survive for millions of years. The direct evidence for that is kind of weak. And certainly if a microbe was at the center of anything larger, a rock larger than about a potato or a golf ball, it could travel through the Earth's atmosphere and land on the Earth, and its envelope would be essentially fried by friction with the Earth's atmosphere, and the interior would get no warmer than room temperature. So a microbe could survive that passage. So because microbes existing within rocks are fairly impervious to the external situation, vacuum, cosmic rays, heat, cold, whatever, that leads to the possibility that life could travel around inside rocks or asteroids. The odds of that life doing other than going between planets in a solar system, like Mars, between Mars and Earth, or Earth and Venus, are very low, because space is so large that once an asteroid or a space rock is flying through interstellar space, the odds of it being captured by another star system are almost infinitesimally low. So the calculations, Jay Milosh did this 10 or 15 years ago, and others have repeated the calculation, suggest that panspermia, the traveling of entombed microbes through interstellar space, is extremely unlikely. Ready for the next question?
Thanks, Chris. All right, the next question is from Nidish, who is a high school student who wants to know how someone could show a college that they are interested in and like astrophysics if they're still only in high school.
Well, it's never too early to start, and I applaud you if you're already managing to take classes in astrophysics in high school. It's hard to do. I think, the easy way to do that is to talk to a an advisor or career counselor in the universities you're interested in, and show them your high school transcript, show them that you've been taking this kind of a class and that you're interested in an astrophysics or astronomy program, and they will take a strong interest in you, I guarantee, because that level of vocational commitment at high school is very unusual, and also because it's hard to take astronomy or astrophysics at high school. So it would definitely give you a leg up, assuming your test scores are good. If you've done extensive reading around the subject and you can turn that into an essay or a personal statement that really conveys your interest in astrophysics, that's even better, and that would be a good suggestion to do. Because again, most high school essays, college admission essays, are not that super well written. So if you can put some work into the writing and show how committed you are to a subject, that also helps your case. So I'd say you're in good shape, because you're ahead of where most students of astronomy are. Even when they come to college, they may not take a serious astrophysics class until their third year. Ready for the next question?
The next question is from Richard, who's on with us live, who asks, can you shed any insight into the concept of dark half magnets that have been in the news recently? They were presented at the Planck conference in Spain, I guess.
Yeah, I'm going to have to punt on that one, so I don't know the reference. I'd have to read the article before I could meaningfully comment on that.
The next question is, can you explain how astronomers understand the shape of the universe? From what I understand, the universe doesn't have a boundary, so what does it mean to say that the universe is flat?
What it means is to say that the geometry of three-dimensional space-time is flat, or Euclidean. So the simplest way of imagining that is if you send two light beams out parallel, then as far as they can travel through space infinitely far and infinitely long, those light beams will never converge or diverge. Whereas if space-time had a curvature, then those light beams would either slowly diverge or slowly converge. Positive curvature means they would converge, and negative curvature means they would diverge. So that's really what it means, and we can't do the sending light beams out into space and seeing the angle between them experiment, but we can use natural astrophysical objects like distant light sources and clusters and galaxies and quasars to do the experiment. And all these experiments do indicate that space is very close to flat, within 1% of being completely flat. Microwave observations of the Big Bang's radiation itself confirm this. Ready for the next question?
All right, this is the final question for today. We're almost out of time. The last question is from Brandon, who asks, if the universe expansion is speeding up, could it eventually end up expanding at near the speed of light in millions of years from now?
Absolutely. The implication of dark energy is a continuously accelerating expansion. So it is absolutely on the cards that if dark energy has the current strength that it has, we observe locally, and that strength in absolute terms does not change over cosmic time, that the accelerating expansion will continue, and that yes, the projection of this time actually varies because we don't know the strength of dark energy very accurately, and you're extrapolating an exponential rate, which is a little unreliable. But in some time, like a fraction of a billion years, maybe half a billion years, the expectation is that space-time will be accelerating at faster than light speed, essentially ripping space-time apart, meaning that there's no causal signals. That would be the end of causal communication of signals through the universe by light, because everything is moving away so fast you cannot maintain communication, and also you cannot see distant objects. There would be nothing to observe for an astronomer with a large telescope. All galaxies would have receded to the point where we could no longer get information from them or see them. It's a good question to finish with. Thanks very much for your attention and your questions. I think we'll go for 3 weeks from now, because 2 weeks from now I'll be traveling again, but we'll look forward to being back with you in a couple of weeks. Goodbye.